recording here? Say good morning, DJ. Just good morning. Thanks.
Grant, I like you, Chad.
It'll be an evening, man.
Yeah.
Still your voice. Okay, we got ways. We got chapter. We're still in chapter 6, guys. We got bending conduits. I hope the bending conduits is a good choice yesterday. The example that we did. Sizing boxes. Chair. I was talking about bending conduits last night. Still in my mind. Okay, let's take a few examples guys about sizing. As designers, people pay us to size things. We're not going to be installing systems. We will be sizing feeders, branch circuits, service, conductors, and overcurrent protection devices. So what I'm going to do, guys, I'm going to take a few seconds here to size, give you typical loads. How would you size a typical load for non-continuous load and a continuous load? Before we talk about continuous, non-continuous, everybody knows what the definition of a continuous load is? Brad? Spencer?
3 hours or more.
Of 3 hours or more of the current, the equipment is running for 3 hours or more continuously, right? There's one more. A lot of people miss it, not just you guys. Max at its rated amps. So if I have a piece of equipment that's rated at 50 amps, Eric, my friend, and that piece of equipment unloaded and it's running at 25 amps, that's not its rated amps. It has to be at its rated amps, which is most of the cases. All right, let's go ahead. So we know what continuous load is. So I'm going to take example number one. Example number one, my friends, it's going to be, and I'm going to be doing a lot of drawing today. So I have a load of 9 amps. I have a 9 amp load. And for this 9 amp load, I need to find first, this is what I need to find, the overcompression device, and second is the conductor. We're going to be sizing overcompression device and conductors for loads. It's a 9 amp. My question for Spencer, just knowing it's 9 amps, does it really matter when I do the sizes right now, if it's single phase, 3-phase, or DC, or whatever? At this point, it really does not matter if it's an AC, DC, if it's at this point, overcompression device and conductors, or 3-phase or 2 phases. So let's go ahead and it's non-continuous. No, this matters. Non-continuous. Okay, the first thing to do when you size as an engineers and designers, they're going to come to you and say, well, why can't you size me, size the conductors and the overcompression device for this equipment? Okay, so number one, everybody knows what this symbol is, that this is bulb. Everybody, that's a symbol for a circuit breaker, right? From now on, just when you see it, you've seen it guys before, every time you see this little deal here, this is a circuit breaker. Every time you see a line like this, Ben, this is not a stick, this is a wire, right? Okay. So overcurrent protection device. Overcompression device. I want to go with the overcompression device. If it's non-continuous, all what I have to do is take the amps, the 9 amps, and take all these 9 amps all the way to 240.6. If you have never been in 240.6, make sure you go there. 240.6 has all the standard non-adjustable circuit breakers and fuses that are made in the continental United States and elsewhere that follows the NEC code book. Let me ask you a question. This is for Mr. Erbab. Is 16 amp circuit breaker a standard circuit breaker? Is 16 amp circuit breaker a standard circuit breaker? How, anybody else can? No? Why?
15.
It's not listed in the NEC code book. Did I tell you it's according to the NEC code book though? That's a tricky one. Well, it is not a standard because it's not listed in the NEC code book. That's a good question, but though it's a very common, 16 amps, guys, is a very common circuit breaker used in Europe and in the Middle East and a lot of places, 16 amps. So the reason why I picked the 16 because but we're not there. The reason why I said that, guys, because you will be working, Brad, in downtown Minneapolis in a firm, and they're doing like LB Beckett, and they're doing projects in United Arab Emirates for the U.S. Army, and you're going to be designing based on. You'll be surprised how close the international system to you that you can imagine. So you're going to be sizing based on not this table, on other tables. So 16 amps. That's why I mentioned these things. You will be if you work for engineering firms like LB Beckett and major ones. They have projects all over the country, and all over the world, as a matter of fact. In Brazil, South America, we did projects there. So anyway, but we're here, we're in the US, sizing based in the US as of now. So 240.6, what would that give you, buddies? What's the next standard overcomputation device? Circuit breaker. 15 amps, thank you. It's a 15 amp. So this boy is going to be a 15 amp. Number 2, let's talk about this GIL then. Next, let's talk about this GIL, which is the conductor. Is the conductor a GIL or a boy? Depends on your point of view. Conductor. Conductor is my wife's description of it, or a wire. These are kind of low-level language. What's the high-level language that we use for this conductor? Based on the code. High-level term. Branch circuit, right? Big word. Branch circuit. It's really just a conductor or conductors. Branch circuit. Can you guys write branch circuits here? This is a branch circuit. Why a branch circuit? Between the utilization equipment and the overcomputation device. That's defined in NEC Code Book Article 100, defining it as a branch circuit. What are the other alternative? Feeders and services. Everybody's okay with that? Camille, Jim, my friends? Okay, so I have a conductor branch circuits, the technical term, wire, if you want to call it. So from here, you're going to take it to table 240, oops, not 240. You're going to take this one to which table? 310.16, soon to be 310.15b, 310.15b16, right? Table 310.16. Which column? Whom am I going to pick? Ryan. Which column are we going to go to? Look at the amps. Your options are 60, 75, or 90. Column meaning the installation. 60. Why 60? Anybody can help Brian or Ryan? Or it's 100 or less. I don't know anything about the termination. Did they tell me the termination? Anything about termination? 100 or less, default to 60. So it is a 60-degree column. And what would that give you guys based on this minimum size conductor that we can use for power and lighting? Not number 16, not number 18. What's the minimum in the NEC code book? Number 12. Number 12. Up to this point, I need number 12. Number 14. I'm sorry. Number 14. Number 14. Now, if it was commercial industrial, the standard in the engineering community, guys, is not to use this than number 12 anyway. But you can, based on the code, you can use number 14. Here's my question for you. How many conductors do I need for this load? Up to this point, that's poor man's or woman's job to say number 14, Chad. It's not enough to write number 14 in your blueprints. Not enough. Two things you need to size it for me. Number one, how many conductors do you need for this load? Based on the info that I gave you guys, do you know how many conductors? Is it single phase? That's where you start asking. Is it single phase, Chad, or 3-phase? Well, let's make this load, since we're in the single phase, let's make it a single phase. Okay, now great. Now we know it's a single phase, right? So how many conductors you need for a single phase load? Minimum. 2 conductors, the hot and the neutral, or the hot and the hot. 2 hots are single phase too. Everybody knows if you take 2 phases, phase A and phase B, what are they called? Not 2 phase. That's single phase. If you take phase A and phase B and feed a machine, what system is that? Single phase. Single phase with 2 hots. If you take a hot and a neutral, what system is that? Single phase, a hot and neutral. So single phase have 2 phases. One phase is 2 phases, and the other phase is a phase and a neutral. How about if you put 3 phases now? It's become 3-phase. Okay, am I clear about this? Or 2 hots. If you have a 2 hots and a 242 hot load, is this single phase or 3-phase? Single phase. Okay, based on this, how many conductors do I need without the ground? Always without the ground, 2 conductors. 2 conductors. And since we are in the sizing business, I'm going to always pull a ground. I'm going to always pull a ground here. This is my number 3. I'm going to call this is number 3. Number 3, always equipment grounding conductor. EGC, equipment grounding conductor. How can I size the equipment grounding conductor for this load? If you are using a pipe, the pipe, especially metallic pipe, that will be the metallic pipe will be your equipment grounding conductor. If you're not, or if you're using PVC, then you need to pull an equipment grounding conductor. If you're using a cable, you need in the cable you need an equipment grounding conductor. Okay, you size the equipment grounding conductor always based on the overcurrent protection device. Always. So what's the overcurrent protection device? 15 amp. Take the 15 amp all the way to table 250.122. This is where we size the equipment grounding conductor for an based on overcurrent protection device based on the NEC code book. Am I too loud for you guys? Sorry. And so we have 15 amps, and you need to go to table 250.122. What's the overcurrent protection device, Holly? The grounding conductor?
14.
Number 14. And if I don't tell you, if you guys go to, when you go to this table, which we have seen before, there's aluminum and copper. If I don't tell you aluminum, what's the assumption in NEC code book? Always copper. We're vested in a copper company. Bet you the guys who wrote the book has some shares in the copper business. Okay, so what size did we say? Number 14. How many? 1. So I need 1 conductor, number 14. AWG, AWG then. This is not $14. AWG, just for the record here. Done. Questions? This is a non-continuous load. This is a non-continuous load. Small load. Would it make a difference had this load, guys, had this load been 100 amps right now? You do the same calculation. 100 amps, you do the same calculation. Do the same calculation. Any question? That's it. They're going to pay you money one day just to do this. Can you believe it?
One referring to next to the 250.12? No, right there, yeah.
250.122. The table. Oh, does it look? I'm sorry. 122. Does it? Table 122. I flunked my English writing classes when I was in high school. Can I move on? DJ.
Yeah, yes, sir.
I said, can I move on, DJ? Okay. All right, let's go to number 2. Here's a number 2. Now let's take another load. And this load this time, it's going to be, I'm going to make this load 113 amps. You guys have a problem with that? I can make any load I want to. And let's make it cool, so make it 3-phase this time. By the way, did I say anything about voltage in the first? Did I say anything about in the first example? Did I say anything about voltage? For all practical reasons, your voltage in that example could be 240, could be 120, could be 480, 2 phases, 480 2 phases, could be any voltage as long as it's 600 volt or less, because almost all the conductors are listed what? 600 volt or less. So if I grab one of these conductors, as long as it's rated, if you look at any of these conductors in front of me here, they're all rated for 600 volt. What does that mean? The same calculation I can do for any voltage up to 600 volts. That's why I didn't put any voltage for these. Do I need a voltage? You don't need a voltage. You can put it at any voltage. Okay? So do I need a voltage here? For practical reasons, this voltage could be any voltage. So I'm not going to put a voltage. So I want to go again. Always, I want to start sizing, guys. I'm going to call this is number 1 this time, just switching track. And I'm going to call this one, this is number 2, that I'm going to size. And the equipment ground conductor, always. I'm going to size an equipment ground conductor. I put it in green, and I'm going to call this boy number 3. Anybody has an issue with that? Cool. 113. And this load is continuous. Continuous. What does continuous means? Fully loaded, running for 3 hours or more. fully loaded, running. Look at these lights. A good example of this, guys. You came here, Brad. You were here at 6:15 when your wife kicked you out of the house. From 6:15 until 9 o'clock now. In a few minutes, it will be 3 hours, and they will be here. They will be on until probably 4 o'clock. These lights. That's a continuous load. So, all right, continuous load. Let's do number one, the conductor, or the fancy name for it, branch circuit. The fancy name, branch circuit. Branch circuit conductors. This is a technical term for it. Okay, branch circuit conductors, continuous load. If it's continuous load, the code says you have to multiply it by 1.25. Why? Why do you guys think they give it 1.25? Safety, caution, because they don't want the conductor to heat up. The more you load conductors with current for a longer period of time, they heat up. Safety. They said here, you know what? We're going to up them a little bit, 25%. Okay. So we take 1.25, multiply it by the full load current, 113. I need a calculator, and I need two gentlemen, or a gentleman and a lady, to agree on this calculation. 141.25. 141.2. Anything less, when I do calculation, guys, anything less than 0.5, drop it. 141. Agreed upon? Two? Okay, amps. Great. And then you take the 141 amps. You're going to take this boy to a table 310.16 under which column and why? Which column and why? 75, why? Over 100. Over 100. See what the rules that we went over yesterday, very important. So we're going to go to 75-degree column. Everybody knows why 75-degree column, Mr. Erbab, because it's more than 100 amp, you go to 75-degree column. Do I hear any answer? 310. What's the, do we have 4 aught? 1 aught? I was up by a couple. How many conductors? Look at the system. 3-phase. I want you to tell me how many conductors. We don't count with it. Did I say I need a neutral? 3-phase. 3-phase assumption is always non-neutral unless they tell you otherwise. Write yourself a note. 3-phase, the assumption is non-neutral for 3-phase loads unless they tell you they need a neutral. Okay? So 3-phase loads, 3 hots, 3 conductors, number 1 aught, and AWG dollars. Number 2. Any question, guys? Straightforward, no gimmicks, nothing. Mr. Erbab, you go to that table 310.16, 75. Why 75? Because it's higher than 100. Chanel, my friend, any questions about that? People will pay you money, guys, to do that. Can you believe that? Ben? Okay, branch circuits, over current protection device. These terms, OCPD, it's like the Twin Cities. If you live in Minnesota and somebody say the Twin Cities and they say the Twin Cities as Bloomington, Richfield, that's a problem. OCPD, somebody said OCPD for an interview, Eric. You go and I tell you, okay, can you size the OCPD for this system? And you say, Chad, excuse me, what is OCPD? You lost the job on the spot. So these are terminology you guys have commonly used, terminology you have to understand. OCPD, over current protection device, a fancy name for 2 things, a fuse or circuit breaker. And if you go fancier, it becomes a relay too. They use relays in high voltage. Okay, so we're going to go the OCPD, the overcurrent protection device. I'm assuming it's going to be a circuit breaker, so I'm just going to put CB, circuit breaker here. Okay, for this, I want to take the same calculation that you did, guys, 1.25, multiply it by 113, equal the same calculation, 141 amp, same calculation. Then I'm going to take 141 amp, now to a different table or article, 240.6 under no column because there's no column, and that should give me 150. Is there any 145? Yes, if you want to custom design yourself one. 250 amp circuit breaker or fuse. In my case, it's a circuit breaker. Oh, 150. Yeah, I was looking at this. 150, thank you. I'm glad one of us is awake. 150. Okay, thanks. 150. I looked at the 240 here instead of looking at the other one. 150. Any question, Mr. Rabab? This is straight from Article 240.6 in the NEC code book. There's a nice little paragraph. I wish they make them a table sometimes. Just a nice little paragraph. Is there any straightforward? There's no gimmicks. The last one, guys, as you might imagine. Where we're going to go? This one. This is what it right here. Okay. The last one, which is number 3, equipment grounding conductor. The same thing. EGC, equipment grounding conductor. Like Amman. If somebody says Amman, it's Minnesota, right? In acronyms for the state. That's like EGC. You have to know it. You come and interview with Chad, and I tell you, how do you size an EGC for this system? And you say, excuse me, Chad, what is this? Go to a different firm. So, how do we size them, guys? We size them based on the overcomputation device. Very easy. What's my overcomputation device? 150? 150 amp. You're going to take this one to which table? 250. Table 250.122. And that will get you a healthy number 6. How many? 1. It's not enough for us as designers, guys, to say just the size. Number 1. And number 6. Number 6, AWG. Right? Okay, so I have a number 6 grounding conductor, equipment grounding conductor, 150 circuit breaker, and 3 conductors, 3-phase, 1 aught each, to feed this piece of equipment that came from China this time, from anywhere else. Any question, guys? Piece of paper. Now, the only thing that's missing out of this, Camille, is the voltage. If I tell you this voltage was 208, would it change any of these calculations? No. If I told you this voltage was 240, same. 600, same. 480, the same. So just write yourself a note here. This calculation could be rated for 208, 3-phase, of course, 480, 240, 600, or any voltage in between. These are the most common voltages that we use in the US, from 208 to 240, 480, 600 volts, because the conductors that we're going to be using, most likely, conductors here are rated for 600 volts. So you can load these conductors up to 600 volts, any of these systems. Now, what's the difference? Then why? Who cares then? Why shouldn't I use any voltages? Why should I use 240 versus 208? Anybody knows? Why should I use 208 versus 240 versus 600? What decided which voltage to use? 2 things. The more power you want, the higher voltage you want to go. Always. The more power in the building you want, the higher voltage you want to go. The lower voltage, the safer. That's something in your mind. Your lower voltage is safer than higher voltage. That's a safety factor. So long story short, if I have my choice, and this machine is my choice in a building, I will wire the whole building with 600 volt and call it a day. Because the conductors will be smaller. I can pump more current in a smaller conductors, more power. But most of the time, guys, is your choices in the US is between 208 and 480, 3-phase. And 208, usually, if you're building as 10,000 square foot or less, most likely it's going to be 208. If it's higher than that, most likely it's going to be 480. So if your building is 480, you really have no choice except to use the 480. So, but choice, if you have the choice, 1,000, 10,000 square foot, generally speaking, or less, 208, 3-phase. Higher than that, it becomes 480. Any questions? Straightforward, no gimmicks, nothing. All right, let's go take another example. Where did we go here? Example number 3. Okay, now we're going to spice it up a little bit. These are non-motor loads, continuous or non-continuous. Let's go through a motor load. What is a motor load? A motor load is any machine or any load that has a motor in it. Okay, almost every machine that you're going to be encountering is a motor load. A fan is a very good example. Blower, air handling unit, pumps. These are all have the major part of the load is a motor. The major part of the load is a motor. Okay. All right. So here's a nice. Look how I changed the symbol for that one. Here's a nice 5 horsepower motor. 5 horsepower motor. And I need to find the overcurrent protection for, oops, let's just continue with the same symbols that we did. And I need to find number 1, number 2, and equivalent grounding conductor, number 3, number 3. Okay, that's the equivalent grounding conductor. And now for motors, guys, because they size them in horsepower, they don't give me the amps, they size them in horsepowers. I have to know the voltage. I need the voltage. So for all practical reasons, let's throw a 240 volt on this motor. 240 single phase. 240 single phase. This is a 240 single phase motor, and I need to size the conductor, and I need to size the equivalent grounding conductor, the overcurrent protection device. The overcurrent protection device, as it shows right now, is a circuit breaker. Circuit breaker, inverse type, 99% of the time, inverse type circuit breakers for this motor. Now, motors are special animals. We're going to cover them, guys, in details next chapter. But for this, I'm just going to throw one example about them. And for motors, we're going to go to Article 430. And I want you to do a couple of things for Article 430. Go with me to page 325, page 324 and 25. In particular, 324. I'm going to be in page 324. Okay, so I have a beautiful motor, pump, blower, what else? Any machine that has a motor, and I need to size the conductor, the overcurrent protection device, the equivalent grounding conductor for this machine. The first thing we do for motors, guys, is find full load current from NEC. To find this one, the first thing you need for motors, to find it, you take the 5 horsepower, and let me just rearrange my stuff here so I have room. You guys, this is, we say 5 horsepower, 240, single phase. The first thing guys you do is find the full load current NEC. What's the full load current NEC? The acceptable full load current based on NEC. For motors, guys, the full load current, they give it to you from the NEC. Because there's so many manufacturers of motors, they don't agree on exactly what the full load current for them. So they group them all in one table. And they said, well, this is the acceptable industry standard that you can use full load current for these motors under these voltages. So if you take the 5 horsepower motor to table, the one that talks about motor single phase is 430.248. So you're going to go to table 430.248. It's a table. Very easy to use. You have rows of horsepower, columns of voltage. Cross-reference the columns and the rows, and that will get you what? Get you the full load current. You have rows of horsepower, columns of voltages. Cross-reference them. You get the full load current of that particular motor at that particular voltage. Okay, based on 5 horsepower motor, and don't forget the voltage is what? 240. What would that give you? How much?
28.
Thank you. 28 what?
Full of
20 load amps, not dollars, nothing. 28 amps. Everybody knows where we got the 28 amps? Very, very important. Okay, now we start our business. Now we start number 1. The first thing is to find the full load current from NEC. That's step 1. Don't do anything. You can't do anything without it. Okay, now I need to find branch circuit conductors. Fancy name, huh? Branch circuit conductors. The code says these motors are considered continuous. You have a pump, you can't tell the pump not to pump less than 3 hours. You know, if you need water, it's going to be pumping. If you need a fan, you can't tell them, okay, I'm going to cool you down, guys, for 2.5 hours, and then I'm going to turn it off. You know, normally you continue with whatever the load was. Yes, sir. Camille?
I answered the question. Which fuel do you think we in?
It's table 430.248. Is that what it was? 248. And 5 horsepower motor with 240. Yeah. If you guys look, good point.
So my question was that you use 240 volts.
Yes. Let me just tell you about the voltages in the table. Very good point. The table voltages, guys, are slightly less than the nominal voltages. There are two types of voltages they use in the industry. The nominal voltage is 240, 480, 208, and there's the equipment voltage. That's confused the people. The equipment voltage, the manufacturer of the equipment designed the equipment to work slightly at a lower voltage because of the voltage drop. For example, if you have a machine, an air handling unit, or a pump, the pump would be rated for 460 voltage and fed from a 480. So there's a difference of 20 volts. Why do you think there's a difference 20 volts? Voltage drop. If there's up to 20 volts voltage drop in the system, the machine will still function perfectly as designed. So my pump is 240. The system that's fit from is 240, but the actual pump most likely it will be rated for 230. Does that make sense? Everybody see the differences? So when I say 240, you go to the table and find the closest voltage to that 240. What closest voltage? And if you don't believe me, if you guys look at the top of that table, it will tell you the range of voltages. Look at the top of the table, and that it says system voltages range from 110 to 120, from 220 to 240. You see it right above the table? So that covers the range of all these voltages. Good point, though. There's no 240 there. There's 230, Chad, right? Because right at the top of the table tell you that's the range that we cover. Okay, so everybody knows why we got 28. That's very important. Let's go size it. Motors are continuous load. Write yourself a note, and then that would be 1.25 multiplied by 28. Who did the answer? Two gentlemen, a gentleman or a lady? 35. When you do your calculation, if it's 35.5, go up. If it's less than 35, 0.5 go down. What is that? 35? Even? 35 amp, great. And then you take the 35 amp, take this one to table, which table? 310.16, and that will get you a healthy number 8. How many? It's not enough to say number 8. How many? 2, right? 2 conductors, number 8, AWG. What insulation? Your designers, what insulation? The assumption it's inside dry location THHN unless you know otherwise. Okay, the assumption is THHN unless you know otherwise. Okay, everybody knows that? Otherwise, if it's a wet location, you just THW or THHW. Any question, guys, about that? So that's perfect here. Number two, we need to find is the overcurrent protection device. Overcurrent protection device. This is a circuit breaker. Why is it a circuit breaker for this motor? Chad Kirby likes circuit breakers. Right? That's the only reason why you have circuit breaker. For this, guys, you need to go to the following. For this one, you need to go to the following. I want you to go to table 430.52. 52. I want you guys to go to table 430.52. Table 430.52. For table, everybody's there? Yes, sir.
Oh, show me where you're getting the 8,000.
So we have 20, 35 up to this.
Oh, okay, so you're just, I see.
And the next.
Going up.
Yeah, because that number 10 can get you 30. You have to go to 35.
Yeah.
Which is number 8. Okay, everybody's at this table. Get in there. Okay, I'm going to talk about this table in details, guys, in a different chapter. So it's coming. But I want you guys to pay attention to two things right now. Number one, the last column. What does the last column say? It says inverse time circuit breaker. That's what we're going to be using. Why? Because I said so at this time. You know, it really is. the inverse type circuit breaker. And the second thing I want you to look at the first column. It says type of motors. What type of motor do we have? Single phase motor. Cross-reference single phase motors with inverse type circuit breaker. What's your percentage multiplier? 250. When it comes to motor, guys, because of the inrush of a motor, for 10 seconds, the motor will suck out of the system 6 times more amps than what's rated for. That's a huge amount of amps. They oversize the circuit breaker so it can handle the inrush, that huge amount of current for a short amount of time. That's called the inrush. Huge amount of current, short amount of time. But if you don't oversize the circuit breakers, what's going to happen to every time you start the motor, circuit breaker will trip. Yes, sir.
Aren't circuit breakers that are made for motors, aren't they made so that they're like timer ones, where they take a certain amount of voltage for just a few seconds longer, or a certain amount of amps for a few seconds longer?
Yes, they're made, all circuit breakers are made, guys, with what we call them inverse current, time current characteristic curve, where as the current go higher, it allows more current to go for a short amount of time. But even with this, just for the inrush, even with this, you still need, because you have no idea who the manufacturer is, you still need to, if I have no idea what the manufacturer of this circuit breaker is, GE, Siemens, Square D, I have no idea. I don't know who the manufacturer of this motor is at the time of the design. What I would do is kind of worst case scenario is go follow what the code says. When you get more information about the motors, you can readjust your design and you go for a lower overcomputation device. You can if you know it, but at the moment of design, most of the time we don't. So my multiplier for this motor is what? 250. So I take 250, 2.5, multiply it by what's the full load current? 28. Thank you. 28, not the 28. What would that give you guys? Even 70 amp even. If 70, yes.
Why are we not using 35 amps?
Because 35 amps is calculated amps for the conductor. We multiply by 1.25.
We're just worried about the motor right now, not
With the conductor. Yeah, we're already finished with the conductor. Otherwise, you'll be oversizing twice. Yes, sir. The 250 is from, are you looking at table 430.252? Cross-reference the last column with the first column. Do you see 250?
Oh, yeah.
250%. 250% is what? 2.5. It's a 250. This is the increase that the code allow you to put on the full load current to accommodate for the inrush. Okay, 70. Then, piece of cake, Chad. Then you take 70 amp, and you take it again. Which article? Come on, Paul, get out of here. 240.6. Always 240.6. What's the standard 240.6? 70 amp. Here's my question for you. What if I did not hit a standard? What if I don't hit a standard? You always go up. So I'm going to put a big arrow here that says, you guys write yourself here, if not a standard, what do you go? Go up. Would that, guys, give you the message? If your calculation end up with a non-standard, like 71 amp, you have 3 options. Either you go to the bar, drink and cry. Option number 1, because now you can't size the circuit breaker. Option number 2, hold a second. Call grandma. Or option number 2 is you go up to the next standard, which is 71, that will make you 80. Do I have an 80 circuit breaker, Holly? Yeah, I have an 80. Or if you don't like to cry, you don't like to go over because it's a protection, custom design yourself. You call Square D, Siemens, and say, can you guys make me a circuit breaker 71 amps? They will be more than happy to charge you 3 times more to make you a circuit breaker 71 amps.
That wouldn't be too efficient though, would it? If you're trying to save money, you'd just be better going up to an 80, wouldn't you?
Yes. Yeah. Yeah. And that's why we stick with the code.
What's the most expensive fuse you've ever blown up from?
Uh, I don't know, I can't remember. Not this time. Fuse. Circuit breakers? I did not trip a whole lot of circuit breakers.
Chuck told me one time you blew up like a really huge one with like a $1,000 circuit breaker or something. They blew it up and it exploded the stuff out on the pole and everything when it went. He said, I've never got to see a big one explode yet.
Yeah, you don't want to see him explode. If you like to see things explode, we'll send you to the military. Okay, 1, 2, 3. Let me size the last one. Any question, guys, so far? Any question? Mr. Irbab, if Chad decided single-handedly to change this from a circuit breaker into a fuse, and a fuse, you guys look at the table. Are you still at table 430.52? If I say I'm going to go to dual element time delay fuse, what's your multiplier? Dual element time delay fuse, 175. Okay. If I said instantaneous trip circuit breaker, 800. If I say non-time delay fuse, 300. We'll talk about these guys, the differences in a different chapter. Okay, the last thing is the ground. I will do my ground, equipment grounding conductor. Okay, how do we size an equipment ground conductor for this boy? How do you size an equipment ground conductor? They're going to pay you to do that. You can call the engineer and say, I'm not an engineer, or you can size it, right?
Right? I'm just gonna use that.
Flip a coin. Okay, we still go to the same overcome protection device, but there's a trick. Let's go to what's the overcome protection device? 70 amp. Take it to the same table 250.1, 2, and 2. Okay, by the way, we're repeating the same article, guys, over and over and over again, right? So, what's the conductor? Number 8. Okay, one conductor, number 8. Okay, one conductor, number 8. Now, listen to me carefully now. One conductor, number 8. So my ground is one conductor, number 8. Because we oversize the overcapacity device for motors, under certain circumstances, this conductor might be number 1-aught. It could be that the grounding conductor is 1-aught and the phase conductors are number 8. It could be, and it will be, if you use certain circuit breakers. The grounding conductor will be 1-aught and the hot conductors will be number 8. What would you do in a situation like this? Here's what the code tells you to do. The code says, no matter what your calculation here ends up, it doesn't have to be more than what the hot conductors are. Please write yourself a note. So no matter what your equipment grounding conductor calculation come up with, you can if you want to, but you do not need to exceed the size of the branch circuit conductors, the HOTs. Did you guys write yourself a note? So EGC, I'm going to write it right here in a different color. I'm going to say EGC, less or equal, come on, Polly. EGC, less or equal to branch circuit conductor. Branch circuit conductor. EGC is less or equal. Everybody knows how to do math, right? Less or equal. What does less or equal? It could be equal or less. Is that a good explanation? Less and equal. It doesn't have to be more. The key point is, now, if Brad single-handedly said, oh, Chad, I'm going to stick with 4-aught, is it wrong? No, you just paid a lot of money for nothing. That, please, for motors, especially for motors, guys, because with motors, because we size for motors, the overcapacity device is way oversized. You could, and you will, end up with an EGC that's twice or one step or 2 steps higher than the phase conductors. They don't want you to go higher than the phase, no matter what. So you use the table, and at the end, check yourself against the size that you came over here. And if it's higher than it, stick with the conductor phase. Are we cool? I can't believe how many people make mistakes with that one.
It's in the article too.
It's in the article, where is
It's
it?
in the 251.22A.
Yep. Let's write it down here. Can you give it to me, please, Holly?
251.22A.
250, 51,
250, 122.
1 dash,
No, it's 122.
oh, 122, 1.
250.122.
I lost my mind here. Okay, where is it? 250.122.8. You don't believe Chad, and I know you guys always believe me. Thank you. 250.1228. 250.1228.
So I got a question.
Yes,
So
sir.
like, because of the inrush current, the 70 amps, you don't have to re-identify your branch circuit conductors to accommodate the 70 amp breaker.
Identify them. What do you mean?
Well, reconfigure them.
Good point. Now, look at this. I have a number 8 conductor. That's where I get all these messages. I told you guys, Chad, you can't believe what I saw. What did you see? I say a number 14 conductors and there's a 40 amp tied to it. It's okay. It's feeding a motor. So a lot of people, if you guys look at number 8, normally number 8 can be protected with what? 40 amps. Right? 40 amps for number 8. Except for motors. No problem. So motors, a 70 amp can protect a number 8 conductor because the circuit breaker here, guys, is meant only for short circuit and ground fault protection. Only here. Why? But the overload, to protect the motor from overload, meaning adding a few amps on the rating of the motor, you use an overload protection on the motor. The motor has 2 types of protection with it. One is a short circuit and ground fault. The other one is a tiny little overload protection. So you highly unlikely you will overload the conductors, because if you overload the motor to overload the conductor, the overload protection of the motor will trip. And if you guys look at, this is how we size the overload. The overload is sized not coincidentally. Look at the conductors are sized with what? With a 25% extra, right? When we size the overload, we size the overload up to 25% extra. Sometimes 115 or 125. We'll size this 115 and 125. No more than 125. So when you size your overload protection right in here, you size it based on maximum of 125. So there you go. So your overload is size 125 and your conductor is size 125. They will match. Meaning you will never ever overload your conductor, because you always have an overload protection that matches the conductor, not the short circuit from the circuit breaker. We will talk about this one in detail. So this is okay.
Overload is signed by the nameplate too, aren't they?
Yes, and they're sized by the nameplate, which makes them a little bit lower even. We'll talk about, guys, sizing the overload for motors in a different chapter. Go. Any question, guys? This is as easy or as hard as it gets. Now, if I give you any motor now, let me tell you, if I give you any voltage, any phase, 3-phase, single phase, or any motor, can you do it exactly 3 steps? Done. The only difference is, Mr. Irbab, if I give you a 3-phase motor, which table are you going to go to? The table in the next page, which is 430.250.250. So you go to a different table because it's 3-phase. The only difference, the same calculation, all the way. 3-phase is 430.250, I believe. Correct me, guys, if I'm wrong here. Yep, 430.250. 5 minutes break. All right.